Hi there, welcome to this Alchemist Chemistry video, which will be a 100% walkthrough of the AQA Combined Science Higher Tier Chemistry Paper 1H. Let's get started. This first question is looking at Mendeleev's version of the periodic table, and the question asks which group of elements has not been discovered when Mendeleev's version of the periodic table was published. If you scan across the elements found within Mendeleev's periodic table, you'll notice that the noble gases are not there. No helium, no neon, no argon. So clearly, group 0 or group 8 elements haven't been discovered by this point, probably down to the fact that they're highly unreactive. So the answer is group 0/group 8. This next part of the question is looking at different models to represent atoms and therefore the history of our discovery of the structure of the atom. And 4 different models have been shown to you. Which model represents the plum pudding model? That was generated by J.J. Thomson, an experimental physicist in 1897. The plum pudding has dried fruit all over the top of the pudding itself. So the model that best represents that sort of image is B. So the answer is B, because J.J. Thomson was responsible for the discovery of electrons, but hadn't yet discovered protons and neutrons found within the nucleus. We're then asked which model resulted from Chadwick's experimental work. Well, Chadwick was working after J.J. Thomson in 1923, and he's credited with the discovery of neutrons. So therefore, we're looking for the model which has not just electrons, but also clearly visible neutrons. The only model we can see that has neutrons is model A, and therefore that would be our answer to this question. Chadwick discovered neutrons, and therefore the model with neutrons is the correct answer. That's A. Question 1 then moves on to isotopes. We're asked to explain what isotopes are, referring to subatomic particles in our answer. Well, isotopes are atoms of elements that have the same number of protons and therefore are the same element, but a different number of neutrons and therefore a different mass number. We have to make reference to subatomic particles, hence same number of protons but a different number of neutrons is what isotopes are. Carrying on with the theme of isotopes, the next question is looking at a relative atomic mass calculation, which is effectively an average calculation involving isotopes and their abundances. So we've been given 2 different isotopes of potassium with mass numbers of 39 and 41 respectively, and to calculate the relative atomic mass, you multiply the mass number by the percentage abundance for each of the isotopes and add those values together. So our working would look a bit like this. Okay, that's the mass times the abundance for isotope 1, added to the mass times the abundance for isotope 2, and divided by the total population or proportion of isotopes present, which will always be 100%. So it's mass times abundance plus mass times abundance for the 2 isotopes divided by 100, giving our answer as 39.138. Now the question wanted us to give our answer to 1 decimal place, so we're going to cut this at 39.1. Because the next subsequent number is not 5 or greater, no need to round, so our answer therefore is 39.1 for the relative atomic mass of potassium from this particular set of data. So question 2 is looking at the properties of acids, and we're using indicators as well. So acids react to produce salts, and we're told we're using a universal indicator as well. Give the colour change when nitric acid is added to a mixture of universal indicator and water. Well, the water itself would be neutral, pH 7, and would appear green. As you added the acid and moved that from neutral to acidic conditions, it would shift from green to red as it became more acidic. So the colour change would be green to red if we added an acid to water. Looking at the next part of the question, we've been asked to say what would happen to the pH of the water when nitric acid is added. Well, again, looking at our pH scale above, moving towards acidity generally causes the pH value to drop, and moving towards alkalinity causes the pH value to rise to a maximum of 14. In the case, because we're moving to a more acidic condition as we're adding nitric acid, we'd expect the pH value to decrease as 1 to 6 is the values of pH given for acidic conditions. And at the bottom of the page, we're asked, what is the state symbol for nitric acid? Well, the nitric acid has been dissolved in water, and therefore the state symbol, which represents substances dissolved in water, is aqueous, or in other words, AQ. We're then told about a reaction between zinc carbonate, a white solid, and nitric acid, forming a salt, zinc nitrate, water, and carbon dioxide. And we're asked to give 2 observations, which we would see when that zinc carbonate was added to nitric acid and the zinc carbonate was allowed to be in excess, i.e. more than enough to go to completion. Well, because we know carbon dioxide gas is being generated, we definitely expect some fizzing. And also, because the zinc carbonate, which is a white solid, is being added into excess, initially the white solid would be disappearing as it reacts to form soluble zinc nitrate, but eventually, once in excess, white solid would then remain and sink to the bottom of the beaker or vessel we're using, because the zinc carbonate is left over, there's in excess, and some is not reacted, and hence it just sinks to the bottom of the container. This final question is an ionic formulae question. We're told the formula of zinc ions is Zn2+, the formula of nitrate polyatomic ions is NO3-. We're asked to work out the formula of the compound zinc nitrate. So, the way to solve an ionic formulae question is to consider that the compound needs to have no overall charge. So if the zinc ions are 2+, and each of the nitrates is -1, how many nitrates will we require to completely cancel out that 2+ charge? We'd need 2 -1s to cancel out a 2+ charge, because that would give us an answer of no overall charge if we did so. And the only formula present which matches that ratio of 1 zinc to 2 nitrates is Zn open brackets NO3 close brackets 2. This formula here. The final part of this question is a 6-marker, and it's a salt making method. We're being asked to prepare a pure dry salt of copper chloride from a chosen acid and a chosen metal oxide. We've got to choose the right acid, the right metal oxide, and go through the method step by step. Let's begin that process. Firstly, the selection of the acid and the metal oxide. To make a chloride salt, we need to use hydrochloric acid, and to ensure it's copper chloride, we need to bring a metal oxide that contains copper. That's copper 2 oxide. The method is as follows. So the first thing we need to do is to measure out a set volume of hydrochloric acid using an appropriate piece of apparatus like a measuring cylinder, and put that into a beaker. We're then going to add in our copper 2 oxide. Now, unfortunately, because copper 2 oxide is insoluble, it won't react particularly quickly with the mainly water-based acid. So we also start to heat and stir the mixture to increase the rate of reaction, and we keep adding the copper 2 oxide until it is in excess, more than enough to go to completion. We don't want to keep that copper 2 oxide, which is now an impurity, so then we filter to remove the excess copper 2 oxide so it won't get caught up with our crystals. And then we will place that copper chloride solution we've collected from the filtration process into an evaporating basin, because it's still full of water, heat and slowly evaporate some of that water to produce something which is known as a saturated solution, a solution which is full of solute at that particular temperature. You can actually prove a solution is saturated by doing a saturation test using a cold glass rod. The cold glass rod will cool down the solution at that particular area, and you should see crystals forming as the solubility of the solute decreases as you put the cold glass rod in, and that helps to prove you're at the saturation point. Then you take your evaporating basin and you leave it somewhere to cool, and as it cools, crystals will form because the solute becomes less soluble in the lowering temperature of the actual solvent itself, of the solution. Filter to collect the copper chloride crystals, so you can collect them, and then finally you dry those crystals using a suitable drying method. That could be just as simple as leaving them somewhere warm, or you might want to dab them with a piece of paper towel to take off any clinging moisture to leave you with pure dry crystals of copper chloride. Question 3 is an energetics question, an energy change question. The student has set up an experiment in which they've placed 100 centimeters cubed of water in a beaker, they've added 10 grams of ammonium nitrate to the water, they've stirred once, and they've measured the temperature of the water over 7 minutes. So, the first question we have is, what is the dependent variable in this investigation? Well, knowing our variables, the independent variable is the one that you change, the dependent variable is the one that you measure, and the control variables are the multiple variables you try and keep the same to ensure a fair test. In this case, we're talking about the dependent variable, the one that you measure, and that would be the temperature of the actual solution itself. We're then asked to give 3 improvements to the investigation to make it more accurate. We want to focus on the experiment itself. There's lots and lots of things you could possibly say here. So we could focus our answer on preventing heat loss, and our answers could include things like adding a lid to prevent evaporation of water and therefore heat loss, insulating the beaker with an insulating material like cotton wool to prevent heat loss via radiation or conduction, or even using a polystyrene cup, which is itself a better insulator than the glass beaker. We could On the other hand, we could focus on improving the method itself. We could stir continuously rather than just once, because that would give us better uniform heat transfer through the liquid. We could repeat the experiment multiple times and take a representative average to give us a more accurate result, or we could use a larger mass of ammonium nitrate, because that would reduce the percentage error in the experiment based around how percentage error works as a calculation. In terms of apparatus we could change or improve, we could use a higher resolution balance or thermometer with a better scale, or we could even use a digital thermometer with a better scale again. We're then presented with the data from the experiment and asked to explain the result. So I've actually highlighted this and broken up into 3 areas of investigation we're going to talk about in the explanation down here. You can see that for the first minute and a half, there seems to be a steady decrease in temperature, and that is implying an endothermic process is taking place. Then at 1.5, there seems to be a sudden change. My guess is that all of the solid is dissolved. And then there's this slowly increasing temperature from 1.5 minutes to 7 minutes. And that's what we're going to really focus on, those 3 areas of the graph. So we'll be saying that from 0 to 1.5 minutes, the temperature is steadily decreasing. Okay, and that must be due to the dissolving of the ammonium nitrate itself being an endothermic process and taking in heat or thermal energy from the surroundings being the water itself that it's dissolving into. Then at 1.5 minutes, there appears to be a sudden change. I guess that's the point at which all of the ammonium nitrate has dissolved and the experiment is actually, the process of dissolving is actually finished. Now, that means from 1.5 minutes to 7 minutes, it's not actually the dissolving of the ammonium nitrate which is important. The rising temperature is because the solution that remains is now slowly absorbing heat energy from its surroundings because the surroundings, the actual room itself, is warmer than the beaker of solution. Effectively, it's just warming up to room temperature slowly over time. The final part of this question is looking at us drawing an energy profile diagram for an exothermic reaction, which try and label on the energy level of the reactants and products, the activation energy, and the overall energy change of the reaction itself. So our diagram would look a bit like this. Okay, so what do we have here? Well, we have our reactant energy line at a higher position than our product energy line, emphasizing that this is an exothermic reaction, which is going to give out energy to the surroundings, so the products will have less energy than the reactants. We have an arrow connecting the reactant line to the product line. That's the enthalpy change, or the overall energy change of the reaction itself. And we have the actual energy profile itself, this hump going up and then falling down. This hump represents the amount of energy we've got to put in to make the reaction actually happen. It's therefore the minimum energy required for the reaction to occur, which is otherwise known as the activation energy. So this is the way an exothermic energy profile diagram would look. If it was endothermic, we'd have to flip around the position of the reactants and products. So it'd be reactants low, products high for endothermic. And for exothermic, it's reactants high, products low. Question 4 is looking at different structural forms or allotropes of carbon. And the first part of the question says, what is the formula of the fullerene Buckminster fullerene? There's only one possible formula for a buckyball or Buckminster fullerene, which is C60. So the correct answer there would be C60. We're then told that graphite is another allotrope or structural form of carbon, and we're asked to explain why graphite can conduct electricity. Well, graphite is a giant covalent structure, which is quite unusual because it possesses delocalized electrons. And it's those delocalized electrons that can flow throughout the graphite structure and conduct an electrical current. So graphite is an unusual non-metal because it's a good conductor, because it has delocalized electrons that can flow throughout the structure and conduct an electrical current. The structural focus question then moves on to alloys, and it says that steel is an alloy of iron and carbon. Explain why steel is harder than soft pure iron. Well, that's because of the nature of how alloys work as structures. Okay, so here's my pure metal with my uniform layers of same-sized iron cations or ions, and here is my alloy with a distortion in those uniform layers because of the presence of the different sized carbon atoms. So carbon atoms are smaller than iron cations in the structure. The carbon atoms are therefore distorting the layers of similarly sized ions. Therefore, the layers of iron cations can't slide over each other as easily as they could in the pure metal, and this creates a more hard and rigid structure, hence why alloys are more rigid and harder than the corresponding metal would be. This next part of the question isn't really a pure chemistry question, it's more of a maths problem-solving question that can sometimes throw at you in these sorts of papers. So a stainless steel fork contains 71.92% by mass iron, and the rest of the mass of the fork is comprised of carbon, chromium, and nickel at these respective masses in grams. I'm being asked to work out the mass of iron X, known as X, in this stainless steel fork. So how will we do this? Well, let's think about this very carefully. If 100% of the mass of the fork is 100%, take away the percentage by mass of the iron, which is 71.92, leaves us with 28.08% of the mass being the carbon, the chromium, and the nickel. And we can also add together the masses of the carbon, chromium, nickel from the table, 0.05, 10.44, and 5.80, telling us that 28.08% is represented by 16.29 grams of mass. So therefore, we can conclude that 28.08% of the mass of the fork is equivalent to 16.29 grams. So if we do 16.29 divided by 28.08, that percentage, we work out effectively what 1% of mass would be. And then if we times that by the percentages of iron present, 71.92, we find out that that would be 41.7228 grams of iron. We basically scale down to 1% and then back up to 71.92% worth of mass. And that means that the iron is this value in grams, but the question wanted the answer probably something sensible like 3 sig fig. So if we cut it there, 3 sig figures, and the next number is a 2, we'd have to round it up, that would be 41.7 grams of iron in this stainless steel fork. Question 5 is looking at the electrolysis of aqueous solutions. So we've been told that we have hydrogen gas and chlorine gas produced when we electrolyze a sodium chloride solution. We're looking at what's going on at the negative electrode, known as the cathode. We've given the half equation what's going on there, which is 2 hydrogen ions are gaining 2 electrons to become hydrogen gas. We ask what type of reaction is this going on at the negative electrode, otherwise known as the cathode. So what I've done is I've written an oil rig, a mnemonic down the side of the page. Oxidation is the loss of electrons, reduction is the gain of electrons. So because the hydrogen ions here are picking up electrons, we would conclude that this is an example of a reduction reaction because there is a gain of electrons by the hydrogen ions as shown by the half equation above. Then being asked to look at the other electrode, the positive electrode known as the anode, and write a half equation for the production of chlorine gas at that electrode. Well, we're told that chlorine gas is Cl2, that's one of our products. We can simply write that in on the right-hand side of the arrow. Now we have a problem here because we have the chlorine molecule contains 2 chlorine atoms, but they were produced by only 1 chloride ion losing electrons. Doesn't make any sense. We need to put 2 in front of those chloride ions, so it now reads 2 chloride ions are becoming chlorine molecule which contains 2 chlorine atoms. That makes sense mathematically, but this is charged and this is not, so we must have lost 2 negative electrons from these 2 chloride ions to become uncharged chlorine atoms found within our chlorine molecule. So we have to make sure those electrons are found on the right hand side of the arrow. If electrons are drawn on the right hand side of an arrow in a half equation, that implies they were lost, not gained. This half equation reads 2 chloride ions are becoming a chlorine molecule because they lost 2 electrons. The chloride ions lost 1 electron each. And finally on question 5, we're told that hydrogen gas and oxygen gas are being produced when you electrolyze a sodium sulfate solution. We're asked to explain how hydrogen gas is produced in the electrolysis of sodium sulfate solution. We have a problem because sodium sulfate, nowhere in that name is there any implication that there's any oxygen going to be produced. So where's it coming from? Well, that's because when we electrolyze solutions, we also have more than just the ions from the compound present. We also have water present, which can break down upon electrolysis into hydrogen ions and hydroxide ions. So water molecules in this aqueous solution are constantly breaking down into hydrogen ions and hydroxide ions. Now, the hydroxide ions actually lose electrons at the positive electrode, the anode, more readily, more easily than the sulfate ions. So they both migrate, they both move over to the anode, but the hydroxide ions find it much easier to lose their electrons to the anode than the sulfate ions. So the OH- ions are attracted towards the positive electrode, the anode, and when they get there, they start to lose electrons at the anode instead of the sulfate ions. And therefore, we could say those hydroxide ions are being oxidized. And the product of that oxidation reaction is oxygen gas, which is then formed and released at the anode. And this half equation here shows the process. We've got 4 hydroxide ions migrating to the anode and forming oxygen gas, water molecules, and we've lost 4 electrons as a part of that process. Question 6 contains some questions focused on an idea known as the conservation of mass. So we have an experiment taking place where a student is heating magnesium ribbon inside a crucible. The magnesium reacts with oxygen to form magnesium oxide. Our question states that they started with 0.12 grams of magnesium and it reacted to produce 0.2 grams of product magnesium oxide. And we are asked to calculate the number of moles of oxygen gas that reacted with the magnesium to form that magnesium oxide, and we've been given the relative mass of oxygen atoms as 16. So this question is an example of us applying the idea of the conservation of matter, or the law of conservation of matter. we know that matter is, or mass is conserved, so whatever the mass of the products must also be equivalent to the mass of the reactants. So if we have 0.2 grams of product, we should have started with 0.2 grams of reactant, but we haven't because we don't know the oxygen, we only know we had 0.12 grams of magnesium. So the rest of the mass to make up to that 0.2 must have come from the oxygen. So if we do 0.2 grams minus 0.12, we know that the missing number, the mass of oxygen, if we follow the law of conservation of matter or mass, should be 0.08 grams because 0.12 plus 0.08 equals 0.2 grams of reactant to match the 0.2 grams of product. So now we know that the oxygen being used was 0.08 grams worth, we can now work out moles, because moles is equal to mass divided by relative mass. We take the mass of oxygen and divide by the relative mass of oxygen molecules, which is 16 times 2, because one oxygen atom's relative mass is 16 and oxygen is O2, so 16 times 2 is 32. So moles equals mass divided by relative mass, and that gives us 0.0025 moles of oxygen present. And that is the answer. The question then says that the student repeated the experiment without the lid on the crucible, and we're asked to suggest why the mass of magnesium oxide would change and be different when the lid wasn't used. Now, most students would have a misconception here and would say, well, the mass would go up because more oxygen can get to the magnesium and increase the amount of magnesium oxide produced. But unfortunately, that's not what's happening because the oxygen was always present in the crucible anyway, and the reaction has generally gone to completion. And if you want to get a bit more oxygen, you can just lift the lid up and put it down again. That wouldn't be the solution for this particular question. Instead, what's going on is that it's likely when the magnesium oxide gets really hot that small amounts of magnesium oxide could ping out of the crucible and escape. So hot magnesium oxide can spit out from the crucible. So the key thing is the product is therefore escaping, and therefore actually would expect the mass to be less than last time, as it's likely some of the magnesium oxide would leave the crucible. The next part of the question is another mathsy question. It's mainly focused on ratios. We're told that copper reacts with oxygen to form copper oxide, and if we had 63.5 grams of copper, it was able to produce 79.5 grams of copper oxide. We're then asked to calculate the mass of copper oxide we'd expect to produce if we only had 0.5 grams of copper reacting with the oxygen. So because we know about the previous experiment, we can apply that to the new scenario. So basically, we want to find out the difference between the 63.5 and the 79.5. If we divide 79.5 by 63.5, we find that it's a difference of a factor of 1.25, pretty much larger. So we multiply 63.5 by 1.2519, etc., then it becomes 79.5. So if we multiply 0.5 grams, our new amount of copper, by that same ratio, that same factor, we can find out the expected amount of copper oxide it should be able to produce, which in this case is 0.62598, etc. And we want the answer to three distinct figures, so we cut it at three distinct fig. Next number being 9, we're going to have to round up the previous digit by 1, so that means we leave our answer as 0.626 grams. It's basically applying the same ratio to the new scenario. This final calculation could be quite tricky, but if you employ an empirical formula-like approach, it becomes much easier to solve. So iron reacts with oxygen to produce an oxide of iron. We're told we have 0.015 moles of iron reacting with 0.010 moles of oxygen gas, which is O2. So if we're going to work out the formula of iron oxide produced, O2 isn't really going to help us. We want to know about oxygen atoms in that formula. So for every 0.01 moles of oxygen molecules, that would be 0.02 moles of oxygen atoms, and that's the number I'm going to use. So we've got 0.015 moles of iron and 0.02 moles of oxygen atoms. Divide them both by whichever number of moles is the smallest, in this case it's the iron's 0.015, gives us the ratio of magnitude of size difference between the number of moles of iron and the number of moles of oxygen. So it's a 1 to 1 and 1/3 ratio difference in terms of iron to oxygen in the expected product's formula. That's no good because that's not a whole number. So we think of a common factor we can multiply both those numbers by to get some whole numbers for our formula. So if I multiply both numbers by 3 to get rid of that third, then it's a 3 to 4 ratio of iron to oxygen rather than a 1 to 1.3, which is really hard to understand, which means the formula of our expected product must be 3 iron 4 oxygen ratio, in other words, Fe3O4. So I wrote that down in the balanced equation space. Now, therefore, if I have iron reacting with oxygen to make this form of iron oxide, there's a 3 in this iron oxide here, so there's 3 ions on this side. I need 3 ions on this side as well, so I put a large coefficient 3 in front of this iron to make sure I had 3 as well on left and right. And there are 4 oxygens in the formula of this iron oxide. So again, if I had just O2, I had to multiply that by 2, coefficient 2 in front, to make sure I had 4 oxygens on the left-hand side to correspond with the 4 oxygens on the right-hand side, and that's how we approach balancing equations. Same number of atoms of different elements on the left-hand side and the right-hand side of the arrow. This final question again leans into the energetics topic, so we're being asked, suggest a reason why methane and oxygen do not react at room temperature. This is kind of kinetics as well. So at room temperature, there must be insufficient energy upon collision for the reaction to be successful. So at room temperature, the molecules are colliding, but with energy below the required activation energies. Therefore, they lack sufficient energy for the collisions to be successful to result in a reaction taking place. Next part of the question is very much looking at trends and patterns. So we've been told that the energy released when methane, ethane, propane are reactive with oxygen has been shown. We're then asked to predict how much energy might be released when butane, the next molecule in the family, is then combusted. Well, we basically look at the change in the energy from each member of the family. So as you move from methane to ethane, the difference is 480. Move from ethane to propane, the difference is 480. So taking that trend forward, if I add 480 onto the 1640 of the propane, I would predict the amount of energy being released by the butane would be 2120 kilojoules per mole, which is our answer, just literally following the pattern shown. This final part of the paper is a bond energy calculation. We've been given the displayed formulae for the reaction of propane with oxygen to form carbon dioxide and water. We've then been told in the question the reaction is overall exothermic, and in the reaction, the energy released when forming new bonds, and therefore the ultimate answer of this whole calculation is minus 1640 kilojoules per mole. I've said minus because we know the process is exothermic and they haven't written it here, but it would be a negative enthalpy change because it's an exothermic reaction. And we're then being asked to calculate the energy of the carbon-carbon bonds missing from this table of information. So what we're going to do is undertake a standard bond energy calculation method, but factor in that we're missing some information in our method. And I'll show you how to do that now. So here we go, folks. Sorry for the crumpled paper. I accidentally just did that. Hopefully it doesn't affect what you can see. So BENAMEX stands for breaking bonds is endothermic and making bonds is exothermic. So that means that when we break bonds in reactants, we have to put in thermal energy. We make bonds in the products, we get out thermal energy. That will become important later on in our calculation. But all I've done here is catalogue all the bonds found within reactants, including our 2 unknown carbon-carbon bonds. So there are 8 carbon-hydrogen bonds in propane, and therefore that's 8 times 410, which is the enthalpy or energy of those bonds, the bond energies for those, giving us this total here. And there are 5 oxygen double bonds present, so that's 5 times 500, and then that's the sum of all these values here. Those are all the bonds being broken, excluding the ones we don't know about yet. Then making bonds exothermic, all the bonds being made in the carbon dioxide and the water. So you can see there are 3 carbon dioxide molecules, that's 6 carbon oxygen double bonds total in those 3 molecules. So 6 times C double bond O, 6 times 740 gives us 4440. And there are 4 water molecules, that's 4 times water, that's 8 OH bonds in total because there are 2 per water molecule. So 8 times OH bonds, 8 times 460, which is the energy of those OH bonds, giving us this number here. The total of all those values is 8,120. So therefore, as a sum, if it's breaking bonds is endothermic and take away the making bonds exothermic negative enthalpy changes from that, it's 5780 plus the unknown 2 carbon-carbon bonds minus the 8,120 for all of the bonds being made is giving us our answer of minus 1,640 as quoted above. So if we add 8,120 to both sides of this equation to remove the minus 8120 from here, so it's gone, but also add it onto this side as well. That means that 5780 plus 2x is equal to 6,480. Now, if we then remove this number here by taking away 5,780 from both sides of the equation, we're left with just 2x being equal to 700. And therefore, we divide by 700 by 2 to find out what x is, our missing number. We find out the energy of a single carbon-carbon bond is going to be 350 kilojoules per mole. And that solves this quite tricky final question on bond energies. I really hope this video helps you to solve this 2021 paper and also future and past AQA combined science higher papers in the future. Best luck with all of that. I hope it goes well in the future for you. Look forward to talking to you in the next Alchemist Chemistry video. Take care. Bye now.